and from observation, we can tell one from the other. We know where it belongs, and so we can figure out how bright. Next chart. There's a great book about Pickering's harem and this whole Harvard College Observatory process called The Glass Universe. Subtitle, How the Ladies of the Harvard Observatory Took the Measure of the Stars. And for those who are into astronomy, astrophysics, you know, spectral classification, OBG, FG, O be a fine girl, kiss me, O be a FGKM, stars. That came out of Pickering's harem. Annie Jump Cannon was one of those ladies that developed stellar classification, which is essentially the stellar temperature scale. Henrietta Leavitt, as I said, did the Cepheids and the distance scale. The American Astronomical Society gives out the Annie Jump Cannon Award. It's a very prestigious award. These were not just housewives doing spare work. These were people who did seminal research that completely revolutionized our understanding of the universe. The book goes into it, it's very good. Okay, so I talked about the 1 over r squared, here's the formula, but basically the two terms, apparent magnitude, that's just how bright it looks to us, okay? Absolute magnitude, that is the intrinsic brightness of the object, and by convention, this is how bright this object would be if it was arbitrarily at a 10 parsec distance from us. Okay, so again, my light bulb, double the distance, quarter the brightness. That defines something called the distance modulus, the difference between how bright it looks versus how bright it basically is. And there's the simple question with the equation with the d for the distance in there, and the fives and the log and all that. That's because, as everybody in this room knows, magnitude, 5 magnitudes, is a factor of 100, and it's an exponential scale. Everybody knows that, right? No. Okay, you weren't the hook. You weren't the only one that said that. A different, yeah, but I know it's a no. The brightness of an object, and to give you a sense, Sirius, the star Sirius, about, help me, -1 brightness, 1.5, something like that. The faintest objects we can see with our eye in a dark sky is about 6th magnitude, if you're under the age of 30. So that's 6, let's call it 6 magnitudes of difference. 5 magnitudes would be a factor of 100. Every magnitude is about a factor of 2.5 in intensity difference, luminosity or brightness difference. So the faintest object you can see with your unaided eye in a dark adapted sky to the star Sirius is a factor of 250 in brightness. Okay, just doing that in my head. That's where these numbers come from. But you can see, I measure this. That's just how bright the object is. It's 13th magnitude, it's 10th magnitude, whatever it is. I know this if it's a Cepheid star because I can measure its period, and therefore I know its luminosity or its brightness, and I can translate to that how bright it would be at 10 parsecs. I can solve for this. There are issues. We're assuming every object, every standard object, like every Cepheid, there's 0 scatter in that curve. It's not 0, it's pretty small in case of Cepheids. We're assuming that the brightness we're seeing is not obscured by dust in the galaxy. So for example, if I went out and I looked at a street light and I measured its brightness, and I went out the next night in a foggy night, and I measured its brightness, it's going to be fainter right? But the light bulb hasn't changed. It's the intervening obscuration. Well, we have the same thing we have to correct for. And at longer distances, I'll get to this shortly, we have cosmological effects. So if, just a conversion scale, but basically a very simple formula. Next chart. Okay, I'm not going to go into this in great detail. If you want the entire transcript, there it is. In 1920, at the Smithsonian in Washington, there was it's called the Great Debate. It's interesting. It's not known as the astronomical Great Debate. It's the Great Debate. And the debate was these small Magellan clouds, Andromeda Nebula, all of these star clouds. Are they part of the Milky Way, or are they island universes, as they were called at the time, beyond our Milky Way? And the prevailing thought was they're in the Milky Way. Just like we had the Orion Nebula in the Milky Way, we had the Andromeda Nebula in the Milky Way. Why? Because nobody knew the distances, okay? And the cosmological thinking at the time was the Milky Way is all there is. So how can anything be much further? Harlow Shapley, this is a little bit older. He was like a 30-year-old cocky kid. And he went up against one of the real, name people. It was a little David and Goliath thing. And nobody knew. The consensus was, I think he won, but nobody knew. Next chart. Is there anybody who's not familiar with the Doppler shift? The change in pitch as a siren approaches.
Well done.
You go now. Okay. So this is the next, enables the next big step. So we're going to talk about redshifts. Remember, so far we started with solar system distances. Then we took a giant leap for nearby stars for parallax, which was just geometry. Then we went to the Cepheids, which are standard candles. And that, because Cepheids are inherently bright stars, although they vary, that pushed us out much further. Now we're going to take another approach, which is the Doppler shift. And so here's a spectrum of the sun. Here's a spectrum of a group of galaxies a billion light years away. Let's just look at the red part of the spectrum. And you see a picture that's a hydrogen alpha line there, for those that have the spectral camera telescopes. And you see it shifting by that amount, okay? That's the Doppler effect, as shown here. And it's a very simple formula. This shift, the change in wavelength over the base wavelength, is equal to the velocity, the radial velocity of the object compared to the speed of light, okay? Now here's where peculiar motions and proper motions come in also, because Doppler shift is only measuring the movement in the radial direction. Okay, it's either coming towards you or going away. And if it's moving transversely, there is no Doppler shift. If it's moving at an angle, then there's a partial, but it doesn't represent the entire velocity. Okay, there's the man of the moment, Edward Hubble. This is a copy of one of the glass plates. This is actually a copy of his discovery plate. By the way, when I was an undergraduate, I worked with glass plates. Everybody familiar with what a glass plate is? Okay, so it's film on glass, basically. And this is what you came up with. And astronomers typically work from negatives, Why? Because it's easier to see a black dot on a white background than a white dot on a black background. This is the core of the Andromeda Galaxy. Everybody knows the Andromeda Galaxy, M31. And you see, this is the date, and you see he crossed out the ends, I forget what the ends were, and he cross-hatched that very faint star there, and he was so excited, he went and got his red marker and said variable. Okay. Exclamation point, because he recognized, probably from comparing with other plates, over the weeks before, that was a Cepheid variable. And that just opened everything up. That one discovery plate made Edwin Hubble. All right? These are his years. He's a very interesting guy. He worked at Princeton most of his professional career. In his younger days, he was a track star of note. And he was an amateur boxer who boxed with, someone's gonna have to help me, Great White Hope. Jack Johnson?
Yeah.
Jack Johnson? He boxed with him. So this guy, he's a pretty athletic guy. And he wasn't sure what to do with his life, and he came to astronomy late, but there's a reason his telescope is up there. He didn't actually own the telescope, but they named it after him. Next chart. So, he measured Doppler shifts of these galaxies. Well, he didn't quite know they were of these clouds, nebula. And because he had discovered Cepheid variable, and that one on the previous one was just the first one, there were more in other galaxies, he was able to plot their distance versus their radial velocity from the Doppler shift. And he developed this curve, and you see there's a lot of scatter, but he said, typically, the further it is, the faster it's moving. Away. Well, okay. Radially, right? Most of them are moving away, but for example, Andromeda is coming right at us. But that's a different story. And yes, it will collide with us. We'll talk about that later if you want. Here's the grand old man in the prime focus cage of the 200-inch telescope. When he did his work, that telescope didn't exist. He used a 100-inch telescope, also in California. But he spent many a night in the dark, exposing these plates, in the cold, suspended in that cage. Has anybody been to the 200-inch telescope? You can look at it. This is like an intelligence question. Would you spend 2 minutes in that cage? I wouldn't put my foot in it. You are way up there, basically suspended. By the way, here's the mirror of the telescope right there.
Oh my God.
You're just floating up there. And they're doing this 10 hours a night by themselves in the cold. You gotta suffer if you want to sing the blues. Next chart. So he came up with Hubble's law. Okay, let's move forward now. We've come up with supernova. And it turns out there are different types of supernova, just like there are different types of stars. And one of them is a type 1A supernova, which happens when you have a binary star, and one of the stars is a white dwarf, an old star, and it starts sucking gas off of its companion and getting more and more bloated, and it reaches a critical mass, about 1.5, actually 1.4 solar masses, and then it supernovas. Because it always happens at the same mass limit, it always has the same brightness when it explodes. What does that tell you? Standard candle. And here is the calibration of the light curves. You can see how tight that correlation is between the brightness and how long since the explosion. So because of that, if you measure a type 1A supernova, you can tell through spectral techniques and others, that is a type 1 supernova as opposed to a different type of supernova. You know how bright it is, and it's just another distance modulus question. You measure its brightness. You see where on that curve it is in terms of how long since it went supernova, days, weeks, and you figure out the distance. Next chart. So here's an example. Here is that other curve, again, in different format, basically a very tight curve. This is the galaxy, a galaxy, there's the supernova. As I think many people here know, when a supernovas becomes essentially as bright as an entire galaxy. We had a supernova 400 years ago in our Milky Way. We could see it, well, it could be seen, none of us saw it. It could be seen in the daytime. Wow. Okay? So these things are very bright. What does that mean? That means we can see them very far away. Next chart. So, remember Hubble's curve with all the scatter. Because of the capabilities of the day, we're talking 1920s, he could see, you know, he had things measured in megaparsecs. This is in gigaparsecs, a billion parsecs. Okay, so his data were only over here. Bigger telescopes, more technology these days, we can see much fainter objects. Same process, and we can see, oh, here's where the data lie. If the universe was just expanding like the Big Bang, it'd be on that blue dotted curve, okay? And according, you see early, close in, you can't tell the difference, right? But you see further, which means, because the technology's improved, which means you see older, and now you see a deviation, and this green curve is based on assumption, a model of a certain amount of dark matter, dark energy, and regular matter. Completely changed our understanding of the universe. If in the days of Hubble, we could see 5% of the mass of the universe, and only that part that was really, in retrospect, very close to us. It was a gigantic step, but it was only the first step. Now, we're looking much further away, and we're seeing things on a very different basis. Next chart, I think this sums it. So there are challenges. I mentioned the issue of fog or dust, changing your measurements. Are standard candles really standard? I showed you that first curve of the Cepheid, then I showed you the more recent, that there are two types of Cepheids. It's okay, as long as you know. Okay, so that's variability in the class. The less variability in the class, the more useful the object is as a standard candle.
And the class is determined by analysis of the spectrum?
For example, yeah. And that's a whole nother discussion. Well, here's another, this is actually an example of class variability. Stars. There are three populations of stars. In standard astronomical form, they have been labeled backwards, just like magnitude goes backwards, right? Population 1, 2, and 3, you would think oldest, middle age, youngest, right? Each population begets the next population. Not the way it is. Oldest, middle age, youngest. Why is this different? Why does this matter? Because in the earliest population of stars, the first population, things were mostly hydrogen and helium. There had not been enough stars to go supernova to create the heavy elements and disperse them through the respective galaxies. Population 2, kind of the sun, yes, that had happened. The sun's about 5 billion years old. it has formed out of material that was processed in earlier supernovas. Population one, well, this going backwards is always confusing. Population one should be the oldest, so it's the youngest. So it has the most metals, as we call everything but hydrogen and helium. And all of that changes the spectrum. And a little bit of the stellar evolution. But fundamentally, that's an example. You look at a star, all stars are not equal age, and so they've been generated, they've created out of different levels of material with different constituent elements. And there's a cosmological redshift. When you start talking about long distances, I'm not going to discuss it, just going to identify it. That Doppler effect, how much of that is because the galaxy is actually receding, physically receding, and how much of that redshift is because the universe is just expanding. And when the universe expands, essentially the ruler for distance expands. It's a very interesting and I think initially confusing concept to wrap your head around. But it's not that the galaxies are expanding into the universe, it's also that the universe itself is expanding. When we do general relativity, we'll talk about that. I think that's not there. Next chart, I think last chart. So, in summary, astronomers developed techniques to measure distances from the Earth and the solar system, galaxies, well, nearby stars, then galaxies, and then as far as we can see, basically, through the universe. It is bootstrapping. Each approach has been built on the calibration and the information from the earlier one. The earlier ones are pretty rock solid. They're just geometry. As you start to push out further and further, you start to bring in some of these other uncertainties that I've alluded to. How standard is a standard candle, for example, but we've learned that the original question we started with, who cares? It's not just we don't want to be the dinosaurs, we want to know when something's approaching. But more fundamentally, for those that care what the universe is made up of, it has shown us that the universe is made up of more than just the stuff we have identified. We don't necessarily know what it is, but we know it's out there through its effects. And that's all because of the distance scale of the universe. And as we go further, just because I have to leave you with a little challenge, what are we going to learn next? Of course, we don't know. If I knew that, I'd be picking up my Nobel Prize. No, I think that's it.
Thank you.
Any other questions? Okay, thank you.
Thank you. Thank you. Well done.